Okay, welcome back, and today we are going to finish the final lesson of the final chapter of this class, and it is going to be about something called Anova, or analysis of variance, and so we call it Anova for short. And this is going to be one test that we're going to use to compare multiple population means, more than two populations. So there are lots of situations where we want to compare and test the difference of means among more than two populations. Okay, and so we're going to use an F-test to do that, but we're going to use an Anova a two-way Anova test that we're going to call. Okay, so again, there's Anova analysis of variance is a method of testing things, and multiple variant or multiple means is one way of doing that. So we're going to start talking about that. So it says the purpose of a one-way Anova test is to determine the existence of a statistically significant difference among several group means. So again, more than two population means. Okay, there must be at least three groups. The test actually uses variances to help determine if the means are equal or not. In order to perform a one-way Anova test, there are 5 basic assumptions that must be fulfilled. Okay, some of these we've seen before. 1, each population from which a sample is taken must be assumed normally distributed. Okay, so normality for each population. All samples are random, that's a given, right? Randomly selected and independent. 3, the populations are assumed to have equal standard deviations or variances. So all the population variances are assumed to be equal. So we call that homoscedasticity. Okay, so we assume that all of the population variances are the same. Okay, so that's one of the key assumptions. 4, the factor is a categorical variable. So again, we're going to use categorical variables in this case. Okay, and 5, the response is a numerical variable. So the factor, so the x variables, are categorical, but the y variable is a numerical or a quantitative variable. Okay, so here's the null and alternative hypotheses in this case. So we're going to have the null is going to be mu1 is equal to mu2, which is equal to mu3, all the way to mu sub n or mu sub k. What do they use here? K. So which is equal to mu sub k. And the alternative is going to be that at least 1 mu is different. And so just like the other tests that we've done that are similar to this test doesn't tell us where the difference lies. It just tells us that there exists a statistical difference. Okay? So now, here's how it works. Here's how the test works. Let me use an example. Let's say I have 3 vats of liquid. And so this represents my 3 populations, right? So in each one, let's say I'm making a liquid that needs a particular concentration of an ingredient, right? So, and for each one of these, I want that the average concentration to be the same for each one, right? So if I'm manufacturing a chemical and it's the same chemical, I want to make sure that all the concentrations are the same, because if it's the same product, I want it consistency, right? Because I don't want to be sending my customers different batches of product that don't have the same concentration, right? So I want the variation to be the same. Okay, so I want the concentration, the average concentration, to be the same. Okay, so I have the average concentration for this one, and this one, and this one. So mu1, mu2, mu3. Now, I have the standard deviation of each one of these populations, right? Sigma 1 squared, sigma 2 squared, and sigma 3 squared, right? So one of the assumptions that we're making is that the standard deviation and the variance of each concentration is the same. So what do we call this is the in-between variation. Or excuse me, I'm sorry, not between, within. So this, and this are called the within variation. Okay, the within variance. But there's also variation in between, right? So there's variation from between these two. There's variation between these two, and there's variation between these two. And so what we call these variations is the between variances. Okay? Now the thing is that under the assumption, right, under one of the main assumptions for doing this test of means, right, the difference of means, is that we're assuming that the population standard deviations are all the same. The variances are all the same. So we're assuming that the within variances are all the same. Now the question is are the between variances are all the same? Well, there's the big idea. If the between variances are very close to each other, and we're doing an F test, then we would expect that the means will all also be very close to each other. Because if these are the same, if these are all the same, and the in-between variances are all the same, then that would mean that the mean concentration should all be the same. Or if these are not the same, if they're far away from each other, or maybe that one of them is different from the others, then that's going to cause a difference between the means. Okay? And that's the idea. So what we're going to do is we're going to use the degrees of freedom of the between variation and the degrees of freedom of the within variation. So that's what we're going to actually compare. That's where the F test comes in. Because what we're going to do is we're going to compare the variance within to the variance between. And so our F statistic is going to end up being our variance of between divided by our variance within. Okay? And what we're going to end up doing is a calculation where, again, the degrees of freedom between, so again, we're going to have degrees of freedom, and the degrees of freedom between is equal to, well, how many things do we have? Well, we're going to have the numerator, and what we're going to talk about is the number of categories. So when it comes to the number of categories, it's the number of vats. So how many categories do we have? We have K, right? So this is going to be the number of categories minus 1. Well, the degrees of freedom for within, that's going to be, because again, we're going to have a sample for this population, we're going to have a sample for this population, and we're going to have a sample for this one. So we're going to have an N1, an N2, and an N3. Well, what we're going to do is we're going to sum up all of these N's, okay? So what we're going to end up with is capital N. We're going to call this capital N. So capital N is going to equal N1 plus N2 plus N3. And then what we're going to do is we're going to subtract off the categories. So the degrees of freedom for the within variation is going to be capital N minus k. Okay, so again, this is going to be the numerator. Oh, let me double check, just make sure. Yep. So this is going to be the numerator degrees of freedom. This is going to be the denominator degrees of freedom. Okay. So the way this works is it's going to be equal to, so the actual calculation is going to be this. It's going to be s squared, the sum of squared error, the sum of squares of the between variation. Okay, so this is b, divided by the degrees of freedom of the numerator, which is going to be k minus 1, divided by, let me write this up a little higher. So I'll say this. So it's going to be s squared b, so the between, divided by k minus 1 degrees of freedom, divided by s within squared, divided by capital N minus k. So that's the calculation for our F statistic. And that's what we're going to use. Okay? So it is an F test that we're doing. But now, again, on the table, if you look at again, this is an output for an Anova table. So again, these are the technical outputs. So notice that the way it's set up is we have the between factor, this is the factor, this is the error. Okay, so this is the between variation and the within variation. And then this is called the SSB and SSW. So this is the sum of squares between the categories, between the populations. This is the sum of squares within each category. And then this is the degrees of freedom for the numerator and the denominator. Okay. Okay, and then this is the MS. This is the mean squared. This is what we're doing. We're taking the sum of squares, dividing by the degrees of freedom of the numerator. This is the mean squares for the between. This is the mean square for the within. So all we're doing is we're taking the sum of squares right here and dividing each by their corresponding degrees of freedom to get these two. And then to get the F statistic, the test value, we divide these two. So again, as you can read this table from right to left, or excuse me, from left to right, we see that this here builds from this. So this divided by this divided by this gives us these two. And then if we divide these two, gives us this, which is our statistic. And then our p-value is calculated accordingly. Okay, so that's how you read the Anova table. Okay, and this is the summary table on the output. Okay, so again, this is the technical. If you use a computer program, this is what you would see. This is what I use a lot. But again, on the calculator, you're not going to see any of this. Okay, so again, this is the calculation that you do. And technically, again, we could call this MSB over MSW. Okay, and this is, again, we could call this SSB and SSW for a sum of square. Okay, but again, the main thing is, what we're testing is the difference between the means, but using variance, the variation within each population, and comparing it to the variation between the populations. Okay, and that's what we're doing. Okay, so now, how do we use the Anova? Well, here's how we do it. Okay, so let me do this. Okay, hold on. Okay. Give me 1 second here. Okay, so I'm not going to go through all the calculations. The main thing I'm going to talk about is the calculator, the Anova test. So here's the example. So it says 4 sororities took a random sample of sisters regarding their grade means for the past term. The results are shown in the following table. So here's the table. So here's the table for each sorority. So we have sorority 1, 2, 3, and 4. So different groups of different sororities. And we have the data, the sample from each sorority. Okay? So pause and write those numbers down. Okay? Or pause and put them in your calculator. So the first thing we're going to do is we're going to take each one of these samples from each one of the populations from each sorority and stick it into a separate list on your calculator. So you could put this in list 1, list 2, list 3, and list 4. So that's what I'm going to do now. Okay? So go ahead and put that data in the calculator, and then what we'll do is we'll explain what's going on in the test and what we're actually testing. So stat edit. Okay, I've got all mine in. Okay, so here's what's going on. So here's what we're doing. It says 4 sororities took a random sample of sisters regarding their grade means for the past term. The results are in the following table. It says, now, using a significance level of 1%, is there a difference in the mean grades among the sororities? Okay, so we want to test the mean grades. So we're looking at a sample of 5 in each of the sororities. And they want to test, is the mean grade for each sorority the same? So a difference of means for the 4 sororities. We want to test this in alpha of equal to 0.01. So we're going to create a Anova table summary. Okay, so here's one way to do it. I'm going to do this on the calculator, and then you're going to see how this works. You're going to get everything you need from the calculator. Okay, so now, all I'm going to do is, now that I've got my list, I'm going to quit out of here, and all you have to do is go to Stat Tests and do the last one, Anova. So if you scroll over to Tests, and there's the Anova function right there at the bottom. Hit Enter, and now all you have to do, here's the cool thing, all you have to do is put in all your lists, followed by commas. So I'm going to put in L1, comma, L2, comma, L3, comma, L4, and then hit Enter. So that's what I'm going to do. And so now look what I get in the output. So notice something here. I get my F statistic. So my F statistic, F star is 2.230. My p-value is 0.1241. So there's my test statistic and my p-value. So I can go ahead and do the test for significance, or the test for the difference of means right there. But also, look what else it gives me. It gives me my factor. Degrees of freedom is 3. So remember what the degrees of freedom is. It's the number of categories minus 1. So my numerator degrees of freedom is 4 sororities minus 1, which is 3. So that makes sense. Now my sum of squares, there's my sum of squares. That's my, again, that's my, calculation, right, for the sum of squares. So 2.88732. Now my mean squared is taking my SS and dividing by the degrees of freedom, which is 3. So there I get my 0.96244. Okay, so now if I scroll down, now it goes to the next part, error. So my error, my degrees of freedom is error, which is 16. Now how to get my 16? Well, how many samples? There's 4 categories, right? Each category has 5, sample size of 5. Well, 4 times 5 is 20, so I have a total of 20 observations among all 4 sororities. Well, if I do n, capital N minus k, well, what's k? 4. So 20 minus 4 is 16. That's where the degrees of freedom come from. And then my sum of squares for the within. So this is the within variation. So that's 6.9044. Again, if I divide that by 16, I get my 0.431525. And then now the S sub x, that's going to be something else. We're not going to deal with that. But again, you get your sum of squares and everything in this output. But the main thing is that we're going to use is the first thing, the test statistic and the p-value. That's really all we need. Okay? But it gives you the whole ANOVA summary table in your calculator. Okay? So just keep that in mind. So now, what do we know? Well, here's the hypothesis test, right? So here we go. So if we were to do the hypothesis testing, it's going to be HO versus HA. And this is going to be mu1 is equal to mu2, which is equal to mu3, which is equal to mu4, versus at least 1 is different. Okay? And what are we claiming? Well, the claim is what? Is there a difference? Okay? So we're going to is there evidence to support this, that there's a difference in the means, the mean grades? Well, step 2 is we're going to assume there is no difference. So we're going to assume the null, right? So we're going to assume that they're all equal. Okay, so 3 is, well, we're going to do an alpha equals what? 0.01. They want a 1% significance level. And here's where I would just write out my data, right? So L1 is my sorority 1 data. L2 is my sorority 2 data. And then L3 is sorority 3, and L4 is my sorority 4 data. Okay, and then all this is going to do is I'm going to stick this into my ANOVA test. And what am I going to get? My F star value turns out to be 2.2303. 2.2. So 2.23. And my p-value equals 0.1241. And that's it. So now I can go to my next step, which is p-value equals 0.1241, which is definitely not less than alpha equal to 0.01. So again, 6 is we fail, right? We fail to reject the null. And so what does that mean for our conclusion? Well, if we fail to reject the null, then there is not enough evidence to support the claim that the mean grades among the 4 sororities is different, okay, based on an alpha level of 0.01 and the sample data. And that's it, guys. That is how you do an ANOVA test to test for the difference of means for multiple populations. In other words, populations bigger than, more than 3, or more than 2 rather, okay? So again, just keep that in mind. That's it. That wraps up everything that we're going to do in this class regarding, and also Chapter 13. So again, there are calculations that you can do, the formulas. I'm not going to go into the formulas because again, we're using the calculator. But the formulas are in the textbook of how you actually calculate the sum of squares. And again, these are formulas that we've seen before, okay? And so, if you know what the factors are, again, so here's the idea. So here's the calculation here, and here's the table, right? So this is a typical ANOVA table summary. So you could use the data from the output of your calculator to fill in a blank table. Now, I don't do that, but I've seen teachers that will do that. I've had teachers that I've taken exam from in graduate school where we'll have to fill in this table. So again, be aware that there are formulas to calculate these, but again, your ANOVA test gives you all of the numbers to fill in this test. And so that's the cool thing about this, okay? Now the formulas for calculating each one of these, like the sum of squares for the between variation and the sum of squares for the within variation, goes back to our talk regarding variation. Okay, so here's the thing. Here's how we calculate. Okay, so we're going to you would use these formulas. Okay, so again, calculating these formulas is tedious. It can be done, but again, you have your calculator. Okay, so SS is your total sum of squares, so the SS total. So you have your total SS, you have your explained variance, which is SS explained, and then you have your unexplained variance. Oh, hold on a second. Make sure that I'm doing the right thing here. Hold on. Yes, okay. Yes, so remember our talk about total variation and explained variation and unexplained variation. That's where these sum of squares come in. So this sum of squares total, the sum of squares between, and the sum of squares within correspond to the total, explained, and unexplained variation. Okay, so this is where we're going to do our calculations. Okay, so again, these are the formulas. We're not going to use them, but again, just so you know. Okay, but that wraps up Chapter 13, and again, that wraps up all of the basic statistics for business statistics or for basic statistics classes that I teach. And if you have any questions, feel free to reach out to me. Again, watch these videos over. Again, if you notice something, if I make a mistake or you have a comment on something, just go ahead and let me know in class or below. So again, I'll talk to you next time. Have a great day.